We have our next test, I think, a week from today. So Tuesday, what's today, the 2nd? So Tuesday, 10/9. Yeah, let's do Monday, 10/9. And if you can't make it Monday night, the day class is doing theirs the next day, Tuesday, 10/10, my anniversary, my 13th. Is that bad luck? 13th in, depends if what? Oh, okay. Okay, well, that makes me feel better. And the topics for exam 2 are everything up through 2D kinematics. So remember, it's cumulative, so there can be old problems on too. So, like always, the way to get ready for it is just to make sure that you understand those practice problems really well. And I would say your goal in working on those problems is you're trying to get to the point where you could explain to somebody how to do one of those problems. And they could say, why is this negative? And you'd say, because of this. And they could say, why is, you have answers. And all those answers would be the correct answers. That's what you're trying to get to. Anybody have any questions about the test? Right, so we're just going to spend some time just doing example problems. So first, let's see. Okay, so we ended last time with that bullet example. So last time we saw that a dropped bullet and a shot bullet, well, let's say a dropped bullet and a bullet fired horizontally would hit the ground at the same time. So now we're going to see what would happen, if you're trying to set up this system. There's going to be some amount of error in how horizontal the gun is when the bullet's shot. So let's say that you're off by 1 degree. That's a pretty tiny angle. How long would it take for the bullet to hit the ground if it's fired 1 degree up? So how long would it take for the bullet to hit the ground? If it's fired 1 degree above horizontal. Again, for last time, we shot it from a height of 1 meter, right? So 1 meter high. Can someone look back and tell me what we're comparing this to? And then how long did it take for the bullet to hit the ground? 0.4 .4515 seconds. Okay, so that's what we're comparing. Okay, so this time the bullet still fired from that Wild West 6-shooter. But this time it makes an angle of 1 degree above horizontal. And the speed is 500 meters per second. Okay, so here's the ground. It's fired from 1 meter high. I'll put the coordinate system on the ground right beneath where the bullet is at time equals 0. So time equals 0 is going to be when it's fired. Time final is when it hits the ground. The origin location, the coordinate system orientation, those are both just shown in that picture. And now we have to think about what we know and want. Do we know anything about the initial position? Yes. 1 meter up, how far horizontally? Yeah, so PIX is 0, PIY is 1. We're trying to find time final. Do we know anything about the final position? Yeah, we do. What do we know? That's right, we only know the y coordinate. So P final y is 0 because it's ending up on the ground. Do we know anything about the initial velocity? Yeah, so we can use the angle and the 500 to figure out the velocity vector. So if you think of this, 1 degree is tiny, so this is exaggerated, but say, so that angle is 1 degree, and think of the coordinate system origin at the tail of the vector. The magnitude of this vector is 500. And so the velocity vector, that initial velocity vector, is 500 times the cosine of 1 degree, 500 times the sine of 1 degree. Can someone calculate that for me? 49, all nines, 0.924. Okay. Oh yeah, 500, not 5. 499.24. Okay. $8.7. Okay, so VIX is 499. I still have something wrong. Yeah. Call that 92. Okay, 499.92 and 8.73. And do we know anything about the final velocity? No. We do know that we don't know that the velocity is going to be 0 when it hits the ground, because we can only do this, like we can only use this analysis until right before it hits the ground. So we don't know what happens, we don't know what that velocity is. We do actually know that the x component of the velocity is going to be the same at the end as it is now, because there's nothing changing the x component of velocity. There's no horizontal acceleration. But let's just leave that off. Putting that in here can just sort of mix you up about what equations you can use and can't use. We'll pretend we don't know anything about the final velocity. And then the acceleration, this is free fall, so AX is 0, AY is 9.81. And is there an equation that works for these? I think this one should. PFY is equal to PIY plus VIY EF plus 1/2 AY TF squared. So 0 is equal to 1 plus 8.73 times time final minus 4.905 times t final squared. How can we solve this for t final? Quadratic. So there's A, there's B, and there's C. Can someone calculate that for me? Okay, so t final is 1.887, and then there's a -1 too. -1.08? Yeah. 0.108. Okay, we're not using negative times, so this is the one we want. And so if you fired a bullet horizontally the same time you dropped it, they would both hit the ground at exactly the same time, and that time would be 0.45 seconds. But if you were barely off in trying to get it horizontal, you were off by 1 degree, and you fired this bullet 1 degree above the horizontal, the time would be multiplied by 4. And the way that works is in this y equation, the only thing that matters is the y component of the initial velocity. If you shoot it totally horizontally, there's no y component, and so it's just like dropping it. But if you're off just a little bit with something going as fast as 500 meters per second, even though you can see the y component is a tiny part of the total magnitude, 8.73 is just a tiny part of 500 meters per second, that's still the same thing as taking an object and throwing it at 8.73 meters per second into the air, which is 20 miles an hour. 20 miles an hour is really small compared to the speed of a bullet, but it's still, if you throw something 20 miles per hour up into the air, it takes a while for it to come back down. So how high will the bullet be at its highest point? Well, again, you can think about this as like we're asking the same question as how high would an object be that you started at 1 meter high and threw straight up into the air at 20 miles per hour? How high would it get? Well, it would get pretty high, And that's the same thing with this bullet. Even though you're shooting it close to horizontally, before it starts to come back down, it's going to be many, many feet in the air, So let's start with these again. The origin and the coordinate system orientation, we can keep those the same. Is there any reason to change either time equals 0 or time final? Yeah, so we'll keep this the same, the instant it's shot, but time final is going to be when it reaches the highest point. And how are we going to specify the highest point? That's right, exactly. The y component of the velocity is equal to 0 at the highest point. Do we know time final? Nope. We knew it for when time final meant something different, but now we don't. Do we know the initial position? Yep, that's the same as it was before. Do we know anything about the final position? We don't know anything about it, but what we're trying to find is PFY. Do we know anything about the initial velocity? That's the same as it was before. VIX is 499.92. VIY is 8.73. Do we know anything about the final velocity? No. What? Yes. Yes. VFY is equal to 0. So that's how we're specifying the highest point. And then the acceleration is still free fall. So 0x, negative 9.81 y. Okay, so is there an equation that works with these? I think this one will probably work. 2 times AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So 2 times negative 9.81. Yeah. Times the quantity PFY minus 1 equal to 0 squared minus 8.73 squared. So negative 19.62 PFY plus 19.62 is equal to negative 8.73 squared. So what's 8.73 squared? And then I guess, okay, so we got negative 19.62 PFY is equal to negative 76 point what? Okay, and then minus 19.62. And can someone solve for PFY? Okay, so positive 4.88 meters, which is like 16 feet or something. So firing this bullet just barely above horizontal, because it goes so fast, before it starts to come back down, it'll get 16 feet up in the air. Any questions about that? Okay. So here's another one. Mm-hmm. We didn't use the fact that the x component of velocity never changes in free fall problems. Okay, so now, let's say, so here's u. Ooh, nice legs. You're sitting on a unicycle. And you're holding a ball, like a ping pong ball. No, something heavier than a ping pong ball. And you're cruising along this way at 5 meters per second, holding the ping pong ball 1 meter off the ground. And over here on the floor is a cup. That's 0.15 meters tall. And the question is, how far away horizontally do you need to release this ball, drop this ball to get it to land in the cup? And then we'll test it with an experiment. Not really, because I don't have a unicycle. Okay, so the question is, what's the distance between the horizontal distance between the ball and the cup that you need to drop the ball so that it lands right in the cup? So how far away horizontally should the ball be dropped so it lands in the cup? Okay, so first thing we have to do is make these 4 choices. I'll just draw the coordinate system. So I'm going to put the y-axis up, and I'm going to put the origin right underneath. If I drew the wrong place. So I'm going to put the origin right underneath the ball at the instant when time is equal to 0, so when it's released. Okay, so time equals 0 is when the ball is released. Time final is when it hits the height of the cup. So you could say reaches a height of 0.15 meters. The origin and the coordinate system are where I drew them in the picture. And now we have to think about what variables we know and what we want. Do we know time final? No. Do we know anything about the initial position? Yes, PIX is 0, PIY is 1. Do we know anything about the final position? Yeah, we know that the Y component is 0.15. We don't know anything about the X component, but that's what we're trying to find. Do we know anything about the initial velocity? So yeah, we do. So I said once before, I think on like a bridge problem or something, if the problem ever says something is dropped, then at the instant it's dropped, its velocity is whatever it's dropped from, the velocity of whatever it's dropped from. So if you're in a car going 50 miles an hour and you drop something, at the instant you let go of it, that thing's going 50 miles an hour horizontally. If you're in an elevator going up, the velocity is the velocity of the elevator. So in this case, so we have to get it in vector components, but the velocity is just going to be 5 meters per second horizontal. So think about that in components. If you know that the velocity vector, okay, so Vix, Viy. If you know that the velocity vector has a magnitude of 5, pointed that way, and you're using a coordinate system oriented like this, what would be the components of that velocity vector? That's right. So that's 5 meters pointing in the positive x direction and nothing in the y direction. So that's just going to be positive 5, 0. So 5, 0. We don't know anything about the final velocity. And then it's free fall, so the x acceleration is 0, the y acceleration is negative 9.81. Is there an equation that'll work with these? There's not. The problem is we don't know time final. So nothing works. And so you do what you always do in that case in 2D. You try to find time final and then use that. Okay, so to find time final, I think this one will work. PFY is equal to PIY plus VIY T final plus 1/2 AY T final squared. So 0.15 is equal to 1 plus VIY is 0, so that whole term is 0, minus 4.905 T final squared. So if you rearrange this, you get 4.905 TF squared is equal to 0.85. So T final squared is 0.85 over 4.905. And can someone take the square root of that? .416 seconds. It's a square root, so that's plus or minus, but with time we always want the positive one. That's not what we were trying to find. So now we need to use that time final to figure out what PFX is. So now PFX is equal to PIX plus VIX T final plus 1/2 AX T final squared. So PFX is equal to 0 plus 5 times 0.416. AX is 0, so this whole term is 0. And so PFX is equal to 2.75. 2.08. I was way off. Meters. Okay, so if you can pedal your unicycle 10 miles an hour, that's pretty fast on a unicycle probably, but and you can measure out, make a mark on the floor, 2.08 meters in front of this cup. Let go of it just as your hand passes it, and it'll fall right in there. Science. Any questions about that? Okay, let me give you one to work on together. So let's say there's this helicopter. Helicopter. And let's say that it's moving 20 degrees above horizontal at 40 meters per second. And an object is dropped from the helicopter and it reaches a height of 30 meters. So first, how high is the object at its highest point? And second, how long will it take for the object to hit the ground? Okay, so before you start working on this, let's talk about like your intuition about what's going to happen here, because I think for a lot of people, you see that first question, part A, and you think, well, the highest point it's going to reach is when it's dropped, you know, because you're 30 meters up in the air, you drop this object, it's going to fall down. Okay. But actually, if you think about the fact that the helicopter is moving at 40 meters per second, 20 degrees above horizontal, this is going to behave exactly the same way as if you took an object from some kind of launcher that's at rest at that point and launched this object at 40 meters per second, 20 degrees above horizontal. And if you think about what would happen if you launched something like that, it sort of then it makes sense to you that it's going to go up a little bit higher before it starts falling back. Okay, that's what's going to happen here because the starting velocity of the object is the same as the velocity of the helicopter, and you know that because it says dropped. Okay, so see if you can work through. Let's just do part A first. I'll give you some time to think about it, and then I'll go through it, and then we'll do part B after that. And talk to each other. Ask me questions if you get stuck. Okay. So first we have to choose time equals 0, time final, origin, and coordinate system. So this is the helicopter. I'll put the coordinate system, the origin on the ground beneath where the object is when it's dropped. Time equals 0 is when the object's dropped. Time final is when it reaches the highest point. And when it gets to the highest point, the way we're going to specify that in the equations is we know that the y component of the velocity has to be 0 at that point. And then the coordinate system is shown. We know time final? No? Do we know anything about the initial position? Yeah, we know a lot about that. So we know it's 30 meters high. Horizontally, what is it? 0, yep. Because that's pretty much how I always choose the coordinate system. If you choose the coordinate system on the ground, right underneath the object at time equals 0, then it's always going to have an x initial position of 0. PIY then is positive 30. Do we know anything about P final? Yeah, we want PFY. Do we know anything about the initial velocity? Yep, that's the velocity of the helicopter. Yep, so that's 40 times cosine of 20 degrees, 40 times sine of 20. What do you get for that? 37.59. 13.68. Do we know anything about the final velocity? Yeah, we know the y component is 0. And then it's free fall, so acceleration is 0 for x and negative 9.81 for y. Is there an equation we can use? I think so. I think, yeah, 2ay times the quantity pfy minus piy is equal to vf squared, vfy squared, minus viy squared. Okay, so 2 times negative 9.81 times the quantity pfy minus 30 is equal to 0 squared minus 13.68 squared. So you get negative 19.62 PFY is equal to, what's 13.68 squared? 187.14, and that's negative. And then minus 2 times 588.6. All right. That's from so you just have to distribute this all out. So we have negative 19.62 times negative 30 gives you a positive, I think that's 588.6, and then subtract it from both sides. Yeah, okay. And so then what's PFY? There's a negative that we're dividing by 2. So 39.54 meters. Okay, so this thing that, this object's dropped out of the helicopter, but because of the velocity of the helicopter, it travels like 30 feet up, that thing from where it's dropped. It goes 30 more feet up straight in the air before it starts coming back down. Okay, so now part B. Do it. Yeah. So how much time does it take for it to hit the ground? How much time from when it's dropped out of the window until it hits the ground? Yeah, I'm doing it. Okay, so this, well, let's think about these first. Usually you don't have to change these between parts A and B and whatever, but in this case, we are going to have to change what time final represents. We'll keep these the same. Time equals 0 can still be when it's dropped, but time final now has to be when it hits the ground. And how are we going to specify when it hits the ground? Yep. P y equals 0. Time final is what we're trying to find. The initial position is still the same. The final position, what do we know about that? The y component, Pfy, is equal to 0. What do we know about the initial velocity? Same as before. Vix 37.59. And what's the y? 13 point what? Okay. Do we know anything about final velocity? No. Secretly we do, but we don't put it in here. Secretly we know that Pfx is 37.59, but that's not useful here. That's just more of like a cocktail party trick. Ax is 0. Ay is negative 9.81. And so the equation that'll work says Pfy is equal to Piy plus Viy Tf plus half Ay Tf squared. So 0 is equal to 30 plus 13.68 Tf minus 4.905 TF squared. And we have to use quadratic formula for that. Could someone calculate that for me? So, okay, so TF is equal to 4.23 and then a negative 1. Some negative something. Anyways, we don't want the negative 1. So this is the one we want. Any questions about that one? PFX would be, like, what does it mean?
No, what number did you say? Like in general, I know you said it was
Oh, I said VFX is the same as VIX. Since acceleration is only happening up, well, down, nothing changes the x components of the velocity. Air resistance really does, but we're ignoring that. So in our calculations, it always stays the same. Yep. Yes. I think the easiest way to think about that is the relationship between coordinates of a point and components of a vector. So like if here's your coordinate system, and you know that the velocity vector looks like this. The components of that vector are just going to be equal to the coordinates of this point. It's 5. There's a distance of 5 out from the origin along the positive x-axis. So it's just going to be 5, 0. And that works along all the, so what if you were riding your unicycle vertically? And that would be your initial velocity. And if you think about the coordinates of that point, in this case, it would be 0, 5. In this case, it would be 5, 0. Now let's think about the two negative directions. So if the unicycle was riding back this direction, no. Okay, so the components of that vector are the coordinates of this point. So that's 5 in the negative x direction and 0, y. So this would be negative 5, 0. Mm-hmm. Yeah, you could use the cosine and sine the same way, and it comes out just the same. Like in this one, that would be 5 times cosine and sine of 180, and it would come out to give you negative 5, 0. Okay. It's just whenever you have them on those 4 axes, it's pretty easy to eyeball it once you get used to doing that. Okay. I guess let me complete this set here with the. Okay, so the last one is like this. That's in the negative y direction, so that would be 0, negative 5. Any other questions? Out there. And so I'm going to say, like, one more thing at the start of class on Thursday, and then that'll be everything that you need for the exam a week from today. What? Yes, today is not Tuesday, it's Monday. So sensitive. So yes, so that's the plan. So we'll finish the stuff for the exam early on Wednesday, and then we'll move on to new stuff when you're done with questions or whatever. So if you have any questions about homework or anything, feel free to bring them on Wednesday and I can answer them. You've seen enough of this stuff to do, I think, all of the 2D kinematics problems.